Hi, I'm Josef.
And I'm Ronnie.
And today we're going to talk about work in progress with Micha Berkus and Ohad Mahmoud about twisted time and the Schwarzian and double-scale SYK.
Double-scale SYK is a chaotic holographic model with a complete UV path integral description. In this poster, we ask the question, how do we obtain the Schwarzian path integral in the IR? We find, and we will show, that the reparameterization of the saddle point solution in the IR acts on twisted time coordinate rather than the ordinary time, as one might expect. Also, in this framework, we can study deformation as multi-Liouville theories and see their IR effect.
So what exactly is double-scale SYK? The SYK model is a quantum mechanical model of random fermion interactions as with a Hamiltonian, as you can see here. And the double-scale limit is simply a limit inside the model which allows you to solve the theory exactly using chord diagram techniques. The thing which we will use is that Stanford has shown this theory is equivalent to a Liouville theory with a certain boundary condition.
We want to see how the Schwarzian emerges in the Liouville formalism in the IR. It's natural to guess that we need to reparameterize the ordinary time coordinates in the center point. But this is wrong since it's violates the boundary condition. What we find is that the Schwarzian arises only from reparameterization of twisted coordinates, which are shown in the equation in the slide. This choice of coordinates is compatible with the boundary condition at low temperatures.
Okay, so let's have a closer look at these twisted coordinates. The integration region is a cutout of a square, as you can see here on the right, and the Schwarzian is essentially just generated by fluctuations of that cutout. The integration region provides some nice features because it supplies a natural UV cutoff and prevents operators from being inserted too close to each other. And it also relates to various phenomena previously discovered in the literature, like the length positivity constraint or the fake disk picture.
Next, we want to formulate the deformation in double-scale SYK in the UV language. In the UV, deformation amounts to adding a random operator to the Hamiltonian. In the double-scale limit, the information is encoded in adding additional chord species and their crossing weights, as shown in the figure. We find that we can also formulate the deformation as multi-field Liouville theory. An example for two fields is shown in the slide.
Okay, so now let's see how these deformations track into the IR. In general, there are two kinds of things which can happen. The first one being that the potential on the soft-mode manifold changes, and the second one that the location of the soft-mode manifold itself can also change inside field space. And using our formalism, we are able to track this second effect now as well. And in fact, we see that it's crucial to understand the IR physics correctly. For example, for deformations with mass dimension between 1 and 3/2, we see that the quadratic spectrum in the IR is given by a non-local theory, as conjectured by Baldassarre, Stanford, and Young. But we also see that the change of the soft-mode manifold is important to ensure positivity of the spectrum.
Now, after we understand the IR structure better, our next step in future work will be to study the holographic properties of such deformations. Especially interesting case is the integrable deformation, where we know that there also exists a not chaotic phase whose holographic properties are unknown.
Thank you for watching.